Okay. Uh, Today's class, let's discuss about Langmuir adsorption method. Uh, if we are looking at the postulates, the surface is homogeneous, all sides are equivalent, and monolayer adsorption is possible. No interaction between the adsorbed molecules on adjacent sites. Heat of adsorption is constant and equivalent for all sides. And adsorbate molecules have a tendency to get adsorbed and desorbed from the surface. These are the postulates of Langmuir adsorption theory. Let's look into the derivation. Derivation of Langmuir adsorption isotherm. So this is based on the one of the postulates, that is dynamic equilibrium exists between the adsorbed gaseous molecule and the free gaseous molecule. Here A is the gas and B is the gas means adsorbent. Adsorption takes place forming a AB1, and A can dissolve on surface of the B, then it's possible to get a gas. Means it's called this backward process is called desorption. Let us consider a surface. This is the surface on which molecules of the gas are condensing and evaporating. That means condensing is called adsorption. Evaporation means it's called desorption. So theta will be the fraction of the total covered at a particular instant. That means theta is the adsorbed, condensed one or adsorbed one. 1 minus theta will be the fraction of the surface still bare. Let's go to the next slide. In the next slide, uh, therefore, rate of evaporation is directly proportional to the theta. Rate of evaporation, if we are removing the directly proportional, then K2 theta. Then where K2 is called a proportionality constant at equilibrium. Then K1P into 1 minus theta is equal to K2 theta. K1P minus K2PT theta, that is equal to K2 theta. Between these two, you can observe that theta is common. So K1P, you can send this minus to the right hand side. Then K1P is equal to theta into K1P plus K2. This K1P plus K2 you can send to the left hand side. Then theta is equal to K1P upon K1P plus K2, that is equal to 6. Now the amount of gas adsorbed per unit mass of the adsorbent, that is x upon m, will be directly proportional to the fraction theta of the surface covered. That is x upon m is directly proportional to the theta. Therefore, x upon m is equal to k into theta. This is equation number 7, where k is proportionality constant. Let's go to the next slide. In the next slide, I'm taking substituting in the next slide. Okay, substituting equation 6 in equation 7, we'll get x upon m is equal to k into k1p upon k1p plus k2. This is further simplification, k into k1p upon k1p plus k2. This is nothing but a k into k1 upon k2 into p, that's upon k1 upon k2 into p plus 1. That therefore kx upon m is equal to ap plus bp plus 1. This is the equation number 8. And here a is nothing but a k into k1 upon k2. B is nothing but a k1 upon k2. The above equation 8 is known as the Langmuir adsorption isotherm. It gives the relation between the amount of gas adsorbed per gram adsorbent and the pressure of a gas at a constant temperature. It gives the better results over a wide range of temperature and pressure. A and B are the constant. So now validity of the Langmuir adsorption isotherm, the above equation number 8 divided by P and then take reciprocal, the result is as P upon X upon M is equal to B upon A into P plus 1 upon A, that is equation 9. Since A and B are the constant, plot the graph P upon X upon M versus P. The nature of the graph is a straight line with the slope equal to V upon A and intercepts on y-axis equal to 1 upon A as shown. This is the one. Intercept is 1 upon A and slope will be V upon A. And this straight line and it intercept y-axis. Then let's look into the drawbacks or the limitations of the Langmuir adsorption isotherm. Holds only at low pressure. Multi-layer adsorption is possible. Ignores adsorbate interactions. Fails to account for the surface roughness of the adsorbent. Then saturation value of the adsorption depends on the temperature. These are the limitations of Langmuir adsorption isotherm. Let's look into the difference between the Langmuir adsorption isotherm and the Freundlich adsorption isotherm. Freundlich adsorption isotherm tells about the quantity of the gas adsorbed by unit mass of the solids adsorbent with the pressure. And Langmuir tells about the number of active sites undergoing adsorption and pressure. Freundlich, represented by the formula x upon m is equal to kp to the power of 1 upon m. Langmuir adsorption represented by the formula theta is equal to kp upon 1 plus kp. Then Freundlich adsorption, heterogeneity of the adsorption site. Langmuir adsorption, homogeneity of the adsorption site. Freundlich one, no information about the adsorption and desorption. Langmuir one, based on the adsorption and desorption equilibrium. So with this, let's move to the one more adsorption isotherm that's called BET adsorption isotherm. If we are looking at the assumptions, the adsorbed layer may be a multi-layer in thickness, since the area availability for the nth layer being equal to the surface covered by the n-1th layer. That means area of nth and n-1th is identical one. Langmuir assumptions apply to each layer. That means solid surface possesses the uniform localized sites. Adsorption at one site does not affect the adsorption in neighboring sites. There is a dynamic equilibrium between the successive layer. That means rate of evaporation from one layer is equal to the rate of adsorption, that's condensation on the preceding layer. The characteristic heat of adsorption is applicable to the first layer only. For a subsequent layer, heat of adsorption is equal to the heat of condensation. These are the few points of assumption. Let's look into the BET equation. BET equation here I am giving the 2, 1. You can write any one. P upon V into P naught minus P, that is equal to 1 upon VMC plus C minus 1 upon VMC, then P upon P naught. So here V is the volume of the gas adsorbed at a given pressure and constant temperature. Vm will be the volume of the gas adsorbed when the surface is completely covered by a unimolecular layer. F is equal to P upon P naught, where P naught is the vapor pressure at the experimental temperature. C will be a constant of a given temperature, that is E exponential E to the power of E1 minus EL upon RT. E1 will be the heat of adsorption of a gas in a first layer. E2 will be the heat of liquefaction of a gas. Let's look into the demerits or limitations of BET equations or BET adsorption isotherm. Surface is assumed to be homogeneous. That's one of the drawback of the BET adsorption isotherm. Then interaction between the adsorbed molecules is neglected. Heat of adsorption from the second layer onwards to be equal to the subsequent layer, which is not usually true. If we are looking at the application of the BET, determining the surface of the solid adsorbent, then solid catalysis can be explained based on the BET. Then determining the inner surface of the hardened cement paste. That's also. Then let's look into the applications of adsorption. Adsorption finds an extensive application in industries as well as in the field of research. Gas mask used by mining area contain activated charcoal which absorbs the toxic gases and allows only the pure air to pass through. Animal charcoal, it is used for the purification of sugar. That means it is used to remove the colored compound. That means it is possible to convert a creamy colored sugar into a colorless or white crystalline sugar one. Then activated charcoal placed between the walls adsorbs gases appearing due to diffusion. Adsorption indicates like acid, fluorides, finds much use in analytical chemistry. Aluminum gels and colloidal silica helps in removing moisture and control humidity in rooms. In ion exchange resins used to get demineralized water also uses the principle of adsorption in softening the hard water by permittivity process. Jewelite uh, adsorbs the calcium and magnesium ions present in the hard one. That means jewelites can remove the what you call calcium and magnesium in the water. Then chromatographic analysis, which is a great important in recovery of the concentrated vitamins and other biological substances, depends on elective absorption of the number of constituents present in the solution of a gas. This is about the absorption. Now onwards, we'll talk about the catalysis. What is catalysis? Catalysis of a chemical reactions increase the rate of a chemical reaction with the help of catalyst. Catalyst increase the rate of a reaction without undergoing any chemical or physical change. Catalyst just decrease the energy barrier of the conversion of the reactant into product. What is catalytic promoter? Give an example. The substance which when mixed in a small amount to the catalyst will increase the efficiency of the catalyst. Such substances called promoters. For example, in the manufacture of ammonia by the Haber process, traces of molybdenum are added to enhance the efficacy of the efficiency of the catalyst. Let's look into the what are catalytic poisoning. Give an example. Impurities present in the reacting gases, even if present in trace amount, decrease the activity of the catalyst by their presence. Such substances are known as catalysts. For example, the efficiency of the platinized asbestos catalyst will be reduced by the presence of arsenic oxide. Impurity in the reacting gases in the contact process of the manufacture of sulfuric acid. What is heterogeneous catalysis? The catalytic process in which the reactants and the catalysts are in different phases is known as the heterogeneous catalysis. Oxidation of sulfur dioxide into sulfur trioxide is the in presence of platinum. Here, platinum is the solid one. Sulfur dioxide is a gas one. Product also gas one. Haber process for the synthesis of ammonia. Here, iron catalyst is a solid one. Sodium and hydrogen are the nitrogen and hydrogen are the gases. Product also gases. Contact process of the process for the manufacture of sulfuric acid. Sulfur dioxide gaseous one react with the oxygen gaseous one in presence of vanadium pentoxide. Vanadium pentoxide is a catalyst and it is a solid gives rise to sulfur trioxide. So these are the few examples and of heterogeneous catalysis. And what is heterogeneous catalysis? Let's look into the homogeneous catalysis. The catalytic process in which the reactants and the catalysts are in the same phase is known as the homogeneous catalysis. For example of homogeneous catalysis is sulfur dioxide react with the water and oxygen in presence of nitric oxide. Nitric oxide is a nitric oxide is a catalyst and the reactants are in the same phase. The obtained product is the sulfuric acid, sulfur dioxide and oxygen here in presence of nitric oxide. It's a gas and giving rise to sulfur trioxide. One more example, carbon monoxide react with the oxygen in presence of nitric oxide, use the carbon dioxide. All are gaseous one means same layer or homogeneous layer. Differentiate between the homogeneous and heterogeneous catalysis. Homogeneous catalysis means when the catalyst and the reactants are in the same phase. the process of catalysis is known as a homogeneous catalysis. Heterogeneous catalysis means the catalytic process in which the reactants and the catalysts are in the different phases is known as the heterogeneous catalysis. Example for come, madam.